This meeting is being recorded. I hope I have your permission to record here. All right, so last class, I went over this inferential statistics cheat sheet. So these four different categories here are for one population, one sample. And then right after that, we started looking at two samples. So last class, I put up the summary for two proportions, which are two different populations, two different samples, and how we do a confidence interval, that crazy formula there, we can just put it in a spreadsheet, or a hypothesis test. So we did a confidence interval last class, I'll review that quick. Then we're gonna do a hypothesis test. These are proportions, right? The percent or fraction of a group that has some characteristic. And we were looking at ICU patients, whether they lived or died based on whether they had an infection or not. And then we'll look at population means, two different population means after this. So last session, what we did is we looked at this data from a hospital where we had patients were in ICU, and either they were in population 1 where they had an infection, and then we looked at in that population, did they live or die? That is this first row here. And we found 24 out of 84 of them died. And somehow my little P's there are missing their hats. These are sample proportions. And then there's the other population where they didn't have an infection, they were in the ICU, and 16 out of 116 died. And so this is our second proportion. And we were wondering if we look at the difference in these proportions, so the difference in the proportion of people with infection who died from the people with no infection that died, what's that confidence interval on the difference? So we calculated that in two different ways, using a stack key simulation by just entering our proportion data. And stack key said that the difference in proportions here, so this is our middle here, this is our estimate of the actual proportion of people in ICU with an infection who died minus the people without an infection who died. So again, a difference in proportions. So this says on average, about 14.8% more people with an infection die than people without. Right, that's what we call a point estimate. So if we were putting this in a hospital newsletter or in the news, we would say it's about 14.8% more of people with an infection die than people without. So that's a concern. However, we have a margin of error here. So the margin of error with this simulation would be the difference of these two divided by 2. So we didn't talk about that last time. Let's do that right now. So if I take the difference in these two, 0.262 minus 0.032, and then cut that in half. I think I can do that without a calculator today. 230 divided by 2 is going to give me 0.115. So this would be my margin of error. So we think the difference in proportions so we don't have a p-value yet. We have to do a hypothesis test for that. So again, that's one of the hard things to think about when we're doing proportions is we have many different p's floating around. We have the population proportion, we have the sample proportion, and when we have hypothesis tests, we have a p-value. And those are three different things. So we're not at the p-value yet. So we think right now that the difference in proportions is about 14.8%. Now that's our middle, but this is the sample data. It's not the actual whole population of ICU patients, right? So we have that margin of error, and that's what we have up here. So plus or minus 11.5%. So one way to state a confidence interval is to state the point estimate, the middle, and then the spread. And then, let's see, hang on a sec. Got it. Yeah, it's hard to keep track of all this stuff. The other way we can state the confidence interval is by stating the lower and upper. And so right now I'm using these numbers here for my lower and upper. Notice the ones underneath are a little bit different. So I could also state my confidence interval by stating the lower, which would be about 3.2%, up to 26.2%. So I can say, again, the difference in proportions of people with an infection who died from the people without an infection who died is around 14%, but I could be about 11.5% off. So we got a pretty big spread there. Another way to state that is I can say the difference in proportions is somewhere between 3.2% and 26.2%. The interesting thing to note here, I mentioned this last time, is a difference of 0 is not in my interval. So is it possible that there is no difference in the death rate of these two groups? The answer is, well, anything's possible, sure. Is it likely that there's no difference in these death rates? The answer is, it's not likely because 0 ain't in my interval. So that's when we go over to the hypothesis test and say, okay, what's the probability 0 is not in the interval here? That's what we're gonna take a look at next. Before I do that though, the numbers below here, we calculated in a spreadsheet using this crazy standard error right here and the same old z-score we've been finding with that norm dist. So we did that last class. And what you'll see is the confidence interval from the simulation is a little bit different than the confidence interval from the normal central limit theorem formulas, but they're pretty darn close. They're in the ballpark. All right, so next we want to run a hypothesis test on this. Oops, wrong page. I need a new page. So I need the original information here. Let's copy and paste a couple things. All right, so we need this. We need the data. So this time we're not going to find a confidence interval, so I'm just going to strike that from the record. I'm not doing that right now. What we do want to find out is there a significant difference in the proportion of people with an infection that died compared to the group without? So is there a significant difference in the proportion of patients with an infection who died than those without an infection who died? So again,
it seems like there's something wrong with that because that status lived, so that total says 40.
oh yeah, I screwed that up in my spreadsheet last time. Thank you for pointing that out. I forgot to fix that. I had moved my data in the table around in the spreadsheet, and when I did that, I screwed some things up. So this should be a total of 160 there, and this one right there should be the 40. Thanks for fixing that for me. I think I fixed that in the spreadsheet that we'll look at in a minute. So again, our two populations here, this one right here, I was calling P proportion with an infection, and that is the 24/84. And then this is the proportion with no infection, and that would be the 16 divided by 116. So a couple other things here. When we looked at these figures right there, and let's get the spreadsheet, I'll share that out with you guys again. One of these tabs. Get too many tabs down here. To proportion confidence interval. That should be this one right here. Okay. So let's share. I'll put this in the chat and in the video. And I'm going to add a couple more tabs to this today for the means. All right, so there's the link to the spreadsheet. And this is the same spreadsheet I linked to last time. I've added a couple of tabs since then. All right, so let's see, what are those proportions? So we have 28.6% for the infected patients with an infection versus 13.8. So 28.6, 13.8. P hat infection is 28.6 versus P hat, the sample proportion without an infection is 13.8. Get that right? 13.8, 20.6, yep. And so that we have a lot of sample statistics here. What is the relevant one in this case? When we look at a difference in proportions, the sample statistic is the difference in your sample proportions. So P, sometimes we call this P1 hat, P2 hat, but now I'm going to call it P uninfected. So that'd be the difference in those two. So what does that come out to be in the spreadsheet? Comes out to be about 14.8. And I should note that these are percents. Typically in the spreadsheet and calculators like StatQ, we have to have them as decimals. So 0.147 would be the better, or 148, better way to state that. So that's the sample statistic. That's a pretty big difference. Okay, so that's the mean difference kind of when we did our confidence interval. So now I'm wondering, boy, it seems like the proportion of people who die with an infection is much higher. So I got to decide what my alternative and null hypotheses are here. And just looking at this data here, I'm kind of wondering, is the proportion with an infection really greater than the proportion without an infection? So I'm going to say that's my alternative hypothesis. So I'm going to state my hypotheses next. My null hypothesis would be there's not a difference. So that's for a difference in means or proportions, that's kind of the standard. That we say for the population, no hat on there, let's just assume there's no difference between them. Alternate way we state that is that the difference is 0, no difference. Often the alternative is that there is a difference, which is kind of what I stated up here in red. That would be a two-tailed test, but I'm looking at this and saying, nah, I think I want to do a right-tailed test. I think it's a lot greater. So that's what my alternative is going to be. So I'm thinking that the proportion of people who died that had an infection is actually much higher than the proportion who died that didn't have an infection right there. If I kind of rewrote it in this other notation, but again, this is the standard way that it's written. But this doesn't give us a number for the null hypothesis, whereas this does over here. So that's one reason I rewrite it, because we need a null value. So that would be saying if I subtract the proportion of non-infection to the other side, PI minus PN is bigger than 0. Okay, so that's that whole greater thing there. Not only do I think there's a difference, I think that the proportion of people in infection die at a higher rate than the people without. Significance level, I'm just going to go with the standard. Alpha is 0.05, 95% significance level. So next thing I need to do is figure out how to do a z-score, and z-scores are almost always the same kind of thing. We take whatever the sample statistic is, we subtract the null value, and we divide by the standard error. And the book gives us the standard error formula. I wrote it down a couple slides back. I'm going to rewrite it here. So, and proportion differences are kind of, I think, one of the trickier ones with the formulas because there's a bunch of things involved. So again, my sample statistic is the PI hat minus PN hat, and that was about 0.148. The null value for difference is we're assuming there's no difference, 0. The standard error, that's a wee bit more complicated. That's going to be this thing we call P hat, not PI hat, not PN hat, just P hat. I'll show you how we get that, times 1 minus P hat over the sample size of the first group plus this thing I'm calling P hat, 1 minus P hat. So we've seen this kind of thing before, divided by the sample size of the second group, and then we take the square root of that whole thing there. Now the P hat is what we call the pooled proportion. And the way it works is the null hypothesis assumes that these two proportions are the same. Okay, so if they're the same, then we have to figure out what is that proportion. And we just go back to our data and say, all right, if there really is no difference, then we just take the total amount who died out of the total amount of people there. And that's how we pull them together. There's no difference, just throw them all together. There's no point in separating them into groups if the groups really don't have a difference. So that's where that comes from.
So the,
oops, yeah.
And I could be way off, so definitely correct me. I thought that the pooled proportion was for pairs. For like when, am I just way off?
Oh, so paired, so that's a whole nother topic we'll get to in a little bit. When we talk about pairing the data, that's when we're looking at a difference in, let's see, the average of the differences of two different measurements. And we will take a look at that next. So that's a different idea. And there is what's called a pooled variance or standard deviation with respect to means. And we'll scratch the surface on that, but we really don't have much time to dive into it. So again, the pooled proportion just means we're assuming with the null hypothesis that the two proportions are the same. So we just take all the people who in whatever category we're looking at and divide by the total. We just put them all together. So for our case here, I think that ended up being 40 over 200. We stuck those together. So let's go back, double check that. So here's all the people who died there, and then divided by the total. Yeah, so that should have been 40 over 200. Sorry, my spreadsheet had that error in it there. So that's what we're assuming. If there's no difference, then we would expect about 20% of patients in the ICU to die, is what that says. Oops, wrong button. And that is this P hat that I'm talking about here. And we don't want to do this by hand. We could plug this into something like Desmos, but it's way more efficient to just plug this into a spreadsheet. So I have this in a spreadsheet already, I believe. Let's go over there and take a look. All right, so let's see. We're doing now a two proportion hypothesis test. So if you're at that spreadsheet I shared earlier, scrolling way over to the right there, it's one of the tabs near the end. And is this the right one? Okay, it is, yeah. So I set it up a little bit different than the confidence interval one. Usually with a hypothesis test, I like to state my hypotheses up front. So I have those here. Here I started with a no difference there, but I'm going to change that right now. And this part doesn't change anything in the calculations. It's just a note to me about what I'm doing. So I'm doing that it's greater than 0, or that my P1 is greater than P2. And then I went and typed in the data. So there were 24 out of 84 in the first population, and this is my infection population. And then I told the spreadsheet to calculate what is 24 over 84 as a decimal. Same thing here, I typed in my 16 and my 116, and then above here it just calculates that proportion, and we've seen that before. So that's my new. The sample statistic, like I mentioned before, that is just the difference in those two above. And the pooled, I had the computer calculate that too by just saying, okay, add up the x's, oops. Add up the x's, so that's the orange and this light purple, and then add up the n's, the blue 84 and the darker purple 12. That gives me my 0.2 that I was looking at before. And I also double checked that total there. I don't actually need that though. All right, next, the standard error. So then I just typed in that crazy formula right there using parentheses as necessary. So I'm just gonna retype that for fun. But the way it works, look back at the notes. In the numerators, we have this pooled proportion times 1 minus the pooled proportion. So this would be assuming there's no difference, what proportion of people died, what proportion of people lived. Divide by the sample size based on those who and what has died. Next, again, pooled proportion died versus lived divided by the number of people who died. This is called the standard error for a difference in proportions. Come over here, please. There you go. So I'm just gonna retype that for fun. So here it says it's about 0.57 for the standard error. And I'm just gonna delete it. So I want to square root, so I use the square root function. And then I just want to take my p hat here and multiply parentheses by 1 minus that p hat. And divide by the first sample size. Plus my p hat again, times, and on a spreadsheet, you got to use an asterisk for times. If you put the parentheses next to something, it gets confused. 1 minus p hat divided by the second sample size. And close the parentheses, and there's my 0.057. The z, like I mentioned before, that z right there is the test statistic. And that is calculated, again, the formula for the test statistic is called the z-score when we're doing proportions. And it's the sample statistic, so that'd be my p hat I minus p hat n minus what the null says, 0, divided by this crazy standard error square root there. So I just have to enter that in. Now note, subtracting 0, nothing changes, but I'm just kind of writing it in the standard form. So that's where this comes from here. So I'm getting a z-score of 2.5. That's a pretty high z-score. It's outside of 2 standard deviations. So I would say, oh, this is interesting. That does seem a bit high for a z-score. And again, because the minus zeros really doesn't do anything, I can just take the difference here, the sample statistic, and divide by the standard error. And so that's my z-score. So I just want to draw a quick picture of where we're at here before I talk about the p-value. And often I draw these pictures to kind of make sure I'm coming up with the right conclusion. So in the middle here, we're assuming there's no difference. We have a alternative hypothesis that the difference in proportions is greater than 0. So that means I'm in the right tail here. And I just calculated a z-score of about a little more than 2.5, I think, right? So there's 1 standard deviation, 2 standard deviations, 3 standard deviations. Those are z-scores. And we calculated here a z-score of about almost 2.6. So our z-score is over here-ish. All right, so that's outside of 2 standard deviations. That's in what we call the unusual range. So that is my z test statistic. And I'm just going to call it about 2.6 for now. And so the p-value is whatever is out here in this tail. So now I got to get a calculator like StatKey or the spreadsheet to do that. And I'll do both here for fun. So in StatKey, I already have the 3 different versions of the formula. Straight norm dist does a left tail, 1 minus the norm dist does a right tail, and then we double one of the above there to do a 2 tail. I'm doing a right tail here. So I'm going to highlight that as my final calculation here. So my p-value is 0.00496. So 0.00496, that's a small p-value. It is definitely less than alpha, which was 0.05, and so the decision would be reject the null hypothesis. Now I got to state what that means in a conclusion. So I do have a pretty big Z. That was my first evidence that I'm saying, okay, something weird's going on here. The difference seems way more than 0. And the p-value says, yeah, that is unusual. Conclusion now. Oh, I said I would do this in StatKey too. So to get the p-value in StatKey, I have to have the Z. StatKey just draws a picture of the p-value for me, which is kind of cute. So let's say my Z-score is 2.5788. So StatKey. Normal dist, because I have a z-score, not a t-score. I'm doing a right tail, and then I just plug in my z there, 2.5788, and StatKey says 0.005. And if we look back at our spreadsheet, 0.005, right? Even if we rounded all the way back out to like the 4th or 5th decimal place, that's probably going to round this up to a 0.005. So StatKey has a little less accuracy, but it's in the ballpark. So it agrees. StatKey agrees. All right, conclusion time. So conclusion is where we say what it means in kind of like plain English. What does it mean to reject the null here? And to do that, I got to know what the heck my variables mean. So just a reminder, we have proportion of patients with an infection who died appears to be greater than the proportion of patients without an infection who died. Too far. All right, conclusion. We have strong evidence because we have a low p-value. That the proportion, and this is really the hardest part, I think, ICU patients with an infection who died is more than the proportion of patients without an infection who died. Usually it takes me a couple of drafts to get this right. I got to reread the descriptions again to come up with this. That's the conclusion. So notice I didn't say reject the null, didn't say I'll accept the alternative. I just said, what does it mean in this case to my final p-value? I don't even need to state the p-value. Just said we have strong evidence that that's the case. So that is a hypothesis test. We strong evidence. Thank you. We have strong evidence. There we go. Apparently I didn't get enough sleep either. All right, so we have strong evidence. Thank you very much for correcting my sentence. Next, we're going to take a look at some means